Welcome to the podcast. This is Mr. White.
And Mr. Johnson.
Today we're going to talk about conservation of momentum. So, Mr. Johnson, on the last podcast, you and we discussed momentum.
Mm-hmm.
What was momentum about?
Well, it was the mass and the velocity of something.
Ooh, mass times velocity. And we didn't want to confuse that with kinetic energy.
Right.
That would have been easy to do.
Mm-hmm.
But today we introduced this concept of conservation. So we've seen that before, right?
Yeah, the last unit with energy.
So we talked about conservation of energy. And in short, I suppose, the initial was equal to the final.
Right.
And in energy, it was sometimes confusing because maybe the students wanted to talk about, well, the initial kinetic energy and the final kinetic energy, but that was too specific.
Mm-hmm.
We just wanted to focus on energy.
Right.
Well, with that said, momentum is actually simpler than that because we have one kind of momentum. There aren't different types. So the initial and the final momentum will be one and the same. And so if you recall, our equation was P equals mv.
Mm-hmm.
Remember, P, I thought maybe was once called progress.
Right.
So if we wanted to math this up a little bit, we would say Pi is equal to Pf.
All right.
Or we would say that the mass times the initial speed is equal to mass times the final speed.
Now, why when you have an initial mass and a final mass?
Well, it's very unlikely that the mass of the object will change.
Okay.
Can't think of too many situations in physics where something gets heavier or gets lighter along the way.
Okay.
So yeah, we really want to focus on the fact that there's two objects.
Mm-hmm.
And so in all of these experiments that we've done, object 1 could be moving, so it could have some momentum, and it would hit object 2, which may be moving or it may not be moving, and we would have to do some addition there. And it could have some final velocity as well. So when we look at a situation with momentum, and I know that that's a math mess right now.
Right.
When we look at a situation with momentum, we would need to focus on all the objects and what's going on before the collision and what's going on after the collision.
Okay.
So those are the items that we really need to concentrate on as far as momentum goes. So I'm not very good, but I always enjoyed playing a game of billiards. And this is all about conservation of momentum, where the change in momentum is equal to 0. So before the cue ball hits and after the cue ball hits.
Right.
Okay. So let's see. If I'm playing pool, I got 5 in the back row, then 4, then 3, then 2, then 1.
Right.
So in the before situation, what's the total momentum of that rack of billiard balls?
Well, I mean, the mass is always going to be what each ball is, and you add all the mass together. But
Okay.
since they're not moving, the velocity being 0, the momentum would be 0.
Right. So that's really important to remember. So while in the beginning of this situation, none of them are moving. So they all have masses which happen to be equal to each other.
Mm-hmm.
Mass is present. The initial velocity of each one of them is 0, so no momentum. So the cue ball goes racing in, and it breaks them apart.
Ah, you're a side hitter, not straight on.
I was a side hitter, yeah.
Oh, okay.
So you hit the rack with the cue ball. What must be true about the final momentum if momentum is in fact conserved?
Well, the final momentum would have to be 0 for each individual pool ball.
Not for each one,
Oh, you were doing a total?
but for the total.
Okay. Then it
Right.
would still have to be 0.
So like after the fact, maybe this ball is moving in that direction, and these things are all zigzag and moving in strange directions. If we were to add up all of these arrows, what we would find is that they would add up to be 0, because the momentum has to be conserved due to momentum conservation. This is also a lot like an explosion. So demolition experts understand how to direct an explosion so that a building collapses straight down.
Right.
Or so that when they investigate the scene of a plane crash or they investigate the scene of a bomb exploding, what they actually do is they take a picture and they recognize, okay, well, this was the building before we started, okay, and it was just sitting here, and this car was parked over there, okay, and there was a tree over here, and they look at the before, and they know that the initial momentum before and the initial momentum after has to be the same. So when there's this debris pile, they're able to put stuff back together in the picture. They can figure out exactly where the explosion was and how much force there was and all of these different items. So conservation of momentum has lots of applications. So if you're thinking forensic science, raise your hand. And if you got your hand raised, you will be taking more physics classes about momentum conservation. So how does this all apply to our car crash? So if we have two cars that are moving towards each other, you guys did this experiment. And here I've got a big car and I've got a little car.
Mm-hmm.
And we can do all kinds of scenarios. We can say, well, they're moving towards each other with the exact same velocities, but just in opposite directions. The question becomes, which car wins the battle here? And we know this from the last two investigations that the
Big car is going to win.
The big car is going to win. And so what will happen here, okay, is that they will experience the same force because of Newton's third law. But this mass will have a much larger change in velocity, okay, than this giant mass will have a very tiny change in velocity, okay? And so this car keeps going forward, and this car will actually change directions, which means the change in v is big.
Mm-hmm.
This also relates to, so we talk about the third law, we talk about momentum being conserved. This also relates to Newton's second law. So tiny mass, big acceleration versus large mass, tiny acceleration. So there's lots of applications here that keep showing up. There's different kinds of collisions, which you guys investigated. There's the kind of collision, okay, where the cars get stuck together. And while the first object and the second object had their own individual initial speeds, in the end they have the same final speed. So it's important when you're reading through a problem or you're trying to answer a question that you ask yourself some simple questions, okay? So in the beginning I had two objects,
right,
but in the end I had one object.
So the two masses added together, then multiplied by the final speed.
Right. And so this all applies to our momentum conservation. So way back in the very first slide, okay, so we would say, well, the initial momentum and the final momentum are equal, okay, and object 1 was moving with some velocity, and object 2 was moving with some velocity, but then they run into each other and they get stuck. So we just add the masses together to try and find the final velocity. So just for simplicity's sake, if we say that each object is the same and has a mass of, let's say, 1 kilogram, and let's say that the first object was moving along at 2 meters per second, and the second object was just sitting there. I just plug numbers in, right? Every time I see an m, I'm going to plug in a 1.
Right.
v1i is 2. Plus 1 times 0, that's nice. 1 plus 1 times vf.
Looks good.
So 2 is equal to 2 vf, and then divide by 2, and the final speed is?
1 meter per second.
And that makes sense. The object got heavier,
right,
so the speed had to decrease.
So it doubled its weight,
halved the speed. So a lot of this, I don't want to call it common sense, but a lot of this, if you just slow down and you look at your numbers, you can take a deep breath, and these problems don't solve themselves, but the answer should make sense when you're done.
And you'd want to list the different variables. Like if you're given mass 1, mass 2, put M1, M2, and
Yep.
write the mass next to it.
And I'm very comfortable with symbols, so I write symbols down. But if you're more comfortable with numbers, by all means, write down numbers. Just be careful, pay attention to the detail of things.
Now, what if one mass is bigger than the other mass and they're going at different speeds?
Okay.
If we were to apply this math problem.
So one mass is bigger than the other.
Right.
So I'm just going to say M1 is 2. I'm going to say M2 is 1.
Mm-hmm.
They're going to at different speeds.
Let's say the bigger one's going faster.
Okay, so V1I, let's just call it 2. I'll put some units out there. And do you want these cars to be going in the same or opposite direction?
Well, we're talking about colliding stuff. Let's go same or
Opposite?
opposite direction.
All right, so then I'm going to have to put a negative sign in front of this because velocity and momentum are vectors.
Mm-hmm.
Okay? And are they going to get stuck together, or are they going to not get stuck together in the end?
Let's say stuck together.
Stuck together, okay. So what we're looking for is the final velocity of the two cars that are stuck together.
Mm-hmm.
So it's the same story. The initial and the final momentum have to be the same. I need to consider everything. So here I am writing out my symbols. Because they're stuck together, I can combine the masses again. And I'm in search of this VF, this final velocity that they share. I don't see any zeros over here. So I can't get away with canceling anything out. But I can just start plugging some stuff in. And something really strange happens in this problem because of the numbers I picked. I want to make sure I wrote all this out right. Oh, no, that doesn't happen. I made a mistake. So, really fast. I wrote down the wrong number, so that's something that you have to pay attention to. So it's 2 times 2 plus 1 times negative 1.
Mm-hmm.
And then it's 2 plus 1 over here times the VF. So I go 4 plus negative 2 is equal to 3 VF. And I divide by 3. And what you're left with is 2/3 a meter of a second.
Or it'd be 0.66.
0.66.
Calculator.
Yeah, you people in your calculators. So there's a lot of ways to do this. This is math heavy, but does the answer make sense? Okay. Did the lighter, did at least one of the objects slow down?
Mm-hmm.
And it did. And so if one of them, or if no of them got slower, then that would be a source of concern. Okay.
And then since you have a positive, it shows that you're still going in the direction of the initial vehicle.
We're going in the direction
the bigger vehicle.
of the bigger vehicle, of the right vehicle.
Mm-hmm.
And we want to be careful with the vehicle that had more initial momentum.
Okay.
That's how we'd want to say that. So I believe that covers everything
Mm-hmm.
about conservation of momentum. In the next podcast, we talk about the event of the collision itself. We've been avoiding that and the forces involved. So signing off, this is Mr. White.
And Mr. Johnson.